So in the last video, we found that the solution of this integral can be found using some manipulations of nested functions, because this function is nested within one another. So for example, the integrand here is f is equal to the natural log of x, take away the natural log of x, so forward to infinite amounts of times, and we get that. And then we found that, hey, we could substitute f in here. But today I want to show you guys that indeed a part of this function diverges and a part of it converges. And the way we are going to be looking at this is by finding a Taylor expansion to the function about the f part of the function. So we use the same rule that we used sort of before. We embed the function within the function. So we get f is equal to the natural log of x minus f. And then we can take the exponential of both sides. We get e to the power of f. That is a weird f right there. Oh dear. A weird f. There you go. Is equal to x minus f. And again, we bring f to the other side. And we get e to the f plus f is equal to x. Now, we know that e to the x is approximately the summation of x to the power of n over n faculty from n is equal to 0 to infinity. So it stands that we can use the same expression for y. So for example, e to the f absolutely converges. E to the f absolutely converges to the sum from n is equal to 0 to infinity of f to the n over n faculty. Okay, and we can prove that indeed this converges by looking at the ratio test, which is an plus 1 over an, and we take the limit as n tends to infinity in this case. So that would mean we get f to the power of n plus 1 divided by n plus 1 factorial divided by f to the n over n factorial. So we can simplify this. We need to take the limit still as n tends to infinity. Forgot to put that part. That is very important. By a bit of manipulation of this function by taking the reciprocal and multiplying the reciprocal of this on the top, we get that the limit as n tends to infinity of f divided by n plus 1. And that is equal to 0, which in terms of the ratio test, we have to have something less than 1. We know that 0 is less than 1, so this converges. Absolutely. Converges. And we know that by theorem of the Taylor polynomial for e to the x. And so it stands for e to the f that this will be true. And now what we can do is we can allow x to equal that. We can allow x to equal f plus this sum from n is equal to 0 to infinity of f to the n over n factorial. Okay? Now, what can we do here? We can observe. In fact, we can observe that this is going to alternate where f is where f is less than 0. Then the sum part, sum alternates. We must also consider that this is about f is equal to 0, and we're assuming that f is equal to 0 is defined on our function defined here. So f is equal to 0 is defined. And when you think about that, what that means is we take e to the 0, so we're going to have an exponentially long thing here where we get e to the 0, that becomes 1, that becomes 1. But that's, yeah, that converges to 1. I'm sure that's how it works there. But we can prove that in the summation here. So the sum alternates as with f is less than 0. So let's take, for example, minus 2. Let's say we have minus 2 to the n over n factorial from the sum as n is equal to 0 to infinity. Then we're going to get something like 1. And then we're going to get a negative here. We're going to get minus 2. And then we're going to get a plus. We're going to square it. We're going to get 4 over 2, which is 2, which cancels that out. And then we get a minus, and we get a minus of a cube of 2. So we get minus 8 divided by n factorial. 3 factorial is 6. And so on. That diverges. And in fact, it diverges to negative infinity. So what that proves is for f that is less than 0, then we cannot evaluate some values because it diverges. So how about f is greater than 0? F is greater or equal to 0. How about that? I can tell you now that this is going to absolutely converge by our test before. In fact, we can say because the sum part converges, this entire thing converges. Converges. And now let's think. We were looking at f is 0. In terms of the log function, that would suggest that x is going to equal 1, right? The natural log of 1 is going to equal 0. Is it true for this statement? Let's have a think. Let's have a think. If f is 0 in this case, then what are we going to get? It's not absolutely clear what we're going to get. But here's the beautiful thing about this function. If I take the first two terms, expand the first two terms, we get 1 plus 2f plus the summation from n is equal to 0 to infinity of f of n over n factorial. In fact, it's not from n is 0 because we've expanded our first two elements. Let's get from n is equal to 2 to infinity. It's still the Taylor polynomial. And if we substitute f is equal to 0 in this case, we get x is equal to 1 plus 2 multiplied by 0 plus the summation from n is equal to 2 to infinity for 0 to the n over n factorial. That is 1. Because that's 0, that's 0, x is equal to 1. So we get 1, 0. As would expect in a single natural log or a single log. Let's have a think. Is the log base 10 of 1, 0? Yes, it is. Is the net log base of 8 of 1, 0? Maybe. But in this case, we're looking at the natural log. Okay, so quite an interesting theorem that we can state that that point is on this function. Is it possible to find any other values of functions, nicer values? That is our next video that we will be doing on this function, where we analytically evaluate this function further.